Great pleasure to have Nico here, and I'm looking forward to your talk.
Thank you, Wolfgang. Thank you for the nice introduction, and thank you the whole Berlin team for running this lecture series. This is a lot of work and brings really together the German robotics community. And I have to say that it is really great to see the diversity of the different research topics which are covered here in the lecture series. And I hope that today I can also contribute in one way or the other to this diversity of research topics. So today I'm going to talk about validation and evaluation of cognitive robots. And this is, I think, a very important topic, but very often a topic which is not really in focus of many of us. I mean, of course, we, as a roboticist, you develop algorithms, you integrate them into systems, and you want to evaluate your system. But when it comes to the validation part and then really to the deployment part into the field, then suddenly new challenges emerges. And I would like to structure my talk in two parts. The first part is mainly on motivating why validation and evaluation is important. I will exemplify this with a couple of case studies. And then the second part will be primarily on recent research results from my research group over the last 3 to 4 years, where we developed a validation and evaluation approach, which is ongoing research. So this is a bit more than the research perspective on that, because in that field, I'm 100% convinced that there's a lot of research opportunities. Okay, having said that, let me start my talk. So we are, as roboticists, interested in developing and researching new capabilities. Yeah? So we are interested in developing new manipulation, perception, and control capabilities. And so I am as well. I'm also interested in these kind of things. And let's say we have here a dual arm mobile manipulator, which is from my lab. And you see here this dual arm mobile manipulator in a fake up factory environment. The green stuff, what you see here on the table, these are real battery cells from a battery production facility from an Austrian battery producer. And in this research project, there was the demand to deploy a robot in case of dangerous situations. When these battery cells catch fire, then it is dangerous to send in a human worker to bring these battery cells to a position where they can safely burn. And so this is a typical robotic application. And yeah, one can, of course, develop accordingly appropriated control and perception algorithms. So we also developed a system like the one here, which is purely based on contact situations. So the robot established contact with the table because it's not camera based. So it has a rough estimate where these battery cells are. Then it aligns to the table, aligns to the table with the end effectors, and then lifts up the battery cells and delivers these battery cells to a safe place to finish the burning. So I think that's a nice application. We are all interested in this kind of application. But as you already saw in this scenario, this is, of course, not a real product. Possibly in the future that will become a product, but it remains in a laboratory situation. So we are in a laboratory environment where we have this low TRL. So the TRL stands for technology readiness level, which is something which has been introduced by NASA many years ago to rank basically technologies and innovations and to have some maturity level. Yeah? So is it fundamental research? Is it already prototyped? Yeah? And having demonstrating a method in a laboratory environment is better than nothing, but it's not yet the TRL which we want to achieve. And in order to demonstrate this low TRL, right, I mean, typically we would perform a single demonstration, maybe multiple demonstrations, but it is a single task, a single robot kind of setting. But ultimately, what we actually want to have is that we deploy the system into the field. So that we go into the real factory environment where, by definition, are different constraints. So that is the operational environment. So that would already, by deploying the system into the field, would imply that we have a higher TRL. But in such a situation, obviously, we are more interested into a higher maturity of the technology because we are thinking also in terms of things like long-term deployment. So we want that this robot is robustly and reliably operating over a long period of time. So that basically means that the service which the robot here provides, namely lifting these battery cells and bringing them to a safe place, that this service is constantly delivered. We are also interested into a variety of tasks and possibly also the collaboration, even or cooperation with robots and humans. And you see here, there's an arrow from the laboratory environment to the operational environment, and there's a question mark. And in order to answer this question mark, well, what we need to have is, in order to go from this low TRL to this high TRL, we need to provide evidences, which are required to move from the lab prototypes into this reliable and safe setting. Okay, but the situation is obviously that this is not the one-way, one direction. It is actually, in fact, a very agile setting where we go from the lab environment to an operational environment and we go actually back. So this is bidirectional by definition, because in the operational environment, we will see that certain things are not working, certain capabilities are not rich enough, or even new technology which is not developed in our lab, but which is developed somewhere else, has been developed and needs to be integrated, and that would be the case where we would actually test this in a lower TRL setting. Okay, but if we want to systematize this a bit, let's have a more detailed look into that. What does this actually in practice entail? In practice, this entails that on the one hand side, we have a problem space. So we want to tackle a very, very concrete robotics problem. And for that, we need to consider at least 3 dimensions. The one is the spectrum of the kind of embodiment, which we consider the kind of environments and associated constraints and the task. And then on the right-hand side, we have the solution space. So these are where the actual technologies are developed, our algorithmic advancements, etc. But this is, of course, a bidirectional relation, because from the problem space, we will impose certain design constraints towards the solution space, and the solution space will also give us, again, constraints in the problem space. So this is a very capability-centric perspective now on the problem. But as soon as we leave the laboratory and we engage in other environments, we suddenly also need to engage with other stakeholders. So what are stakeholders? So there's even an ISO standard for this. So stakeholders are individual or organizations having a right, share, claim, or interest in a system or its characteristic in order to meet their expectations and their needs. And we will find these stakeholders also on the problem space, because these are end users. They come up with a certain set of requirements, but we will also have other end users like regulators, certification bodies, etc. And they need to be considered in one way or another, as they also impose certain design constraints on the solution space. And then in the solution space, roboticists working on the behavior, on core functions or complete integrated systems, they need to take this constraints into account when developing such a system. Okay, so what does this now mean in terms of the research challenges which are associated with such a starting point? Yeah? So in a setting where we want to go from prototypes to products, there are certain research challenges associated with, specifically in the field of robot software engineering. So the first thing is that what we would like to do is we want to structure this transition, yeah? To structure this transition from a lab environment of a low TRL to a higher TRL. So we need to have a certain process model or a certain methodology. Yeah. So this does not mean that this is a very rigid thing, but we need to have at least some methodology in place in order to achieve that. And what is actually happening in this methodology? And there are at least, I'm going to focus today in my talk about three things. Yeah? There is more, right? But in today's talk, I look at three things. The first step is we need to have validation in place. Yeah. So the validation basically means that we need to make sure that, or we need to ensure that the specifications of our intended behavior, that they are met. Yeah? Here, the specifications, they can remain on different levels of abstraction. This depends significantly from the kind of stakeholder requirements we do actually have. But this is a process which we need to ensure. Otherwise, we cannot say in the problem space whether we have achieved something or not. The second thing is evaluation. Yeah. So we want to make statements about how good is something. Yeah. So, and this should be exactly the thing where we actually collect evidences, where we can draw conclusions, and this is typically done through a lot of variability, different kind of scenarios, different kind of settings, where we can actually also draw some statistical conclusions about it. Because very often it is the case that we have an assumption that how something will work, but just in the field, and then by trying out in several configurations, several trials, we get a better understanding of that behavior. And then the third thing is that these are important activities. This is also done. Yeah, but in order to really scale that, we need to have automation in place. Yeah, so we need to have automation which goes along the validation and evaluation cycles and make these possible, that we have machines or setups where certain parts of this validation and evaluation can be actually performed in an automated manner due to the, on the one hand, due to the size and scale of the problem, but also due to the capabilities and resources which we actually have. So here automation is a key component into to move forward here. Okay, having said that, let me now introduce you an approach which we call a scenario-based validation and evaluation of cognitive robots, which tries to provide a methodology to actually carry out this validation and evaluation in an automated manner. And to do so, let me introduce you another real-world case study. So there was a time, there was COVID. Maybe some of you remember. And in my former institution, we had a startup company developing mobile robot platforms, omnidirectional mobile platforms, as you see here on the picture. And of course, COVID also was a time of many opportunities. And there was the time where one thought, okay, that COVID is spread through contact infections. Yeah? And as we know from other diseases, if you expose certain surfaces with UVC light with a different intensity and depending on the surface characteristic, of course, and all these things, you can significantly reduce the amount of viruses and bacteria on surfaces. So the idea was for this company, to take their mobile robot platform, to put some UVC lamps on it, and to deploy such a system in public environments, things like healthcare facilities, nursing homes, kindergarten, schools, etc., and to perform disinfection missions. So what does this mean? So the robot is located somewhere in the building where there's a charging station. The robot navigates to a specific target location and then follows a certain disinfection route. So either disinfection route is predefined, or the robot is capable to infer this disinfection route on its own by spotting, for example, specific surfaces which are critically. So critical surfaces could be door handles and table surfaces which are touched, etc. And then after finishing this disinfection route, so during this disinfection, the robot would approach the surface, would expose UVC light to it for a certain duration, and then would move to the next spot. So in essence, this is a rather simple waypoint following task, but of course the intelligent thing here is then, okay, how long should one stop at a certain surface and should disinfect the surface for a certain period of time? And then after this task is finished, the robot would navigate home. Okay, so in such a setting, we need to answer a very important question, namely, how do we know that this robot is safe to deploy? And safety here has actually two dimensions. The first dimension is that UVC light is dangerous for humans. So if there are humans around, so the idea is to deploy this robot in a human populated environment, such a hospital or a nursing home. So there would be the idea either that the robot is operating just at night, but also during the day. If then during the day and there are people around, the robot should not expose the UVC light to humans, at least not for a very long period. That is one dimension. So we need to make sure that there's people detection and these kind of things in place, and that we have mechanisms to turn on and off the UVC lamps, etc. But then there's also a second dimension, which is the safety critical one, that is rooted in the robot mission itself. What does this mean? Because the robot task, the robot mission here in that case, is safety critical on its own. Because there is a certain assumption that the robot is reliably operating in that environment, that the surfaces are to a certain degree free from viruses and bacteria, etc. So we have a certain quality imagination about how clean is the surface, how clean is that environment, how contaminated is it. And that is per se critical, because we could then say, okay, maybe in such a setting, it's fine that also vulnerable people are walking around, etc. Right? And if this would not be the case, then this would be very critical. Okay, so there are these two dimensions. So during the time when this company actually developed this robot, I observed a very interesting thing, which I thought would be an opportunity to investigate further, right? So the company basically, they were located in one of our labs at the university, and they had an environment where they actually tested the basic capabilities of the robot. So they basically came up with a test environment, which was a real laboratory environment, where they tested the different capabilities of the robot, the disinfection and the navigation and so forth. And in a first starting point, they tried out certain missions in this small environment, and then at some point they wanted to go to the hospital, and the next step, which was in terms of scale, similar to the hospital, was the ground floor of the university, which is a 7,000 square meter environment. And the small red box, what you see here, is actually where the laboratory is located. So we wonder, okay, how do you go now from this laboratory environment to this operational environment, and how do you test the robot really in the field? And apparently that is also a problem for other companies and settings. So we did an empirical study. So we performed interviews with robot software developers about their testing practices in the field. We looked into what are the actual test products which the developers produce. So we looked at the ROS spec files, we looked into the GitHub issues, we looked into the test reports, incident reports, test runs, depending on certain configurations, and we looked into these test products. And we try to identify what are actually the core challenges and what is the state of the practice in performing a field test in robotics. And we derived basically three things. So what was quite interesting to see is that obviously through the scale of the environment, it was clear that they cannot test in every location. So what they did was in order to deal with this complexity was an explorative test case design. So they employed certain partitioning algorithms in order to decompose certain parts, certain characteristics into environments, and then try to employ similarities measures like, okay, this looks very similar to another environment, so we don't need to test here again. But even if with these ad hoc approaches to dealing with the complexity, there's a significant cost of the testing. So first of all, there's, from a rather practical side, very few means to perform manual traceability. What I mean here with traceability is going from the requirements actually really to the test results and see whether the requirements have been fulfilled. This should be done in a traceable manner, so that I can know directly infer which of the requirements have been fulfilled, which have not fulfilled, etc. And to which degree I have these requirements fulfilled, meaning how many test runs I have performed to test this specific requirement. And there's also a lack of real-world test inputs. I think this is nowadays a bit changing now if you look to the attempts in the field of large vision language models, the robot foundation models, where also now data becomes a bit more available. But another challenge which remains is the question of the oracle. So the oracle is the entity which says, okay, test has been passed or not, right? So coming up with these unique pass or fail criteria is extremely challenging. Because, well, what does it mean it was a near collision? What does it mean I have completed my mission in a certain period of time, right? What is acceptable and what is not acceptable? And here again, human developer effort is actually required in order to come up with these oracles. And these oracles are then in the end computer programs which check the test output and check for passing or failing. So these are things which still need to be developed by hand. Okay, so taking from this empirical insight, one idea now is that we say, okay, there are actually two dimensions in coming up with this test and validation campaigns. There's the one dimension which is actually the scenario. So this is the outline, or if you here on the right hand side here, this is Romeo and Juliet. the cover from Romeo and Juliet from Shakespeare. So if you take this analogy, if you take in performance arts, an actor would read this outline written by Shakespeare in that case, and it would be a synopsis of the play and a sequence of the possible events when imagined, and an author would write such a scenario, right? Shakespeare, or a robot developer would actually come up with these scenarios. And then on the other hand, we have the actual agent which executes these scenarios. So in performance art, this would be the actor. But there's an interpretation happening, right? So from this outline, we have a more declarative and abstract, we have a more imperative and concrete thing. And is it possible, we ask ourselves, is it possible to provide such a thing also for robotics and then specifically for testing robotic systems? And that is our executable scenario framework or methodology, which basically entails 3 stages. The first stage is the specification of these scenarios, which should be not only on the declarative side, but also on the imperative side, meaning that they are executable. And these scenarios, they should entail at least 3 elements: information about the actor, actually, the kind of play or the behavior in the robotic sense, and information about the environment. And then we have an execution and an analysis stage. But just with the specification of the robot behavior and the environment, we cannot perform any analysis. But what is then required are our acceptance criteria. So these are the specification of our pass or fail settings. And having that, we can then bring that together and say, okay, to which degree has been this achieved or has been this not achieved? And the third stage is then, if we take multiple, and you see this is a feedback loop here, if we have multiple of these executions, we might be able to draw conclusions about the performance of our robotic system. And in order to do this, then this is then the generalization stage, where we say, okay, we have performed these kind of scenarios, we have observed the following behavior, and now these are the conclusions which we can draw from it. Okay, let's have a look how this looks now concretely. And I will provide an example from the case of specifying specifically now the environment. By just specifying the environment, we can do already interesting things. So based on these interviews, we asked ourselves, okay, how can we actually specify these sceneries? So I mentioned already, when it comes to managing this environmental complexity, one statement was, okay, partitioning the environment was another way to handle environmental complexity. So the developers, they went to the environment, looked to specific characteristics, as here in the quotation. Characteristics of each area or room allowed developers to deliberately control the difficulty level. Meaning, okay, maybe we start with very simple scenarios or environmental models here in that case, and we progressively increase the complexity. So in order to do that, there's a specification step, and we developed a domain-specific language. So this is our floor plan domain-specific language. This is a declarative specification language specifically for mobile robots operating in indoor environments. And this gives a developer a mean to express their environments in a very declarative manner. And having such a model representation, we are now then able to automatically, through means of model-to-model generations, to generate artifacts which are necessary for automated simulation. So these could be, for example, 3D wall meshes or grid maps, which can be used by the navigation stack of a mobile robot system. Okay, but this is not sufficient. What is then on top actually required and the floor plan actually allows us to do is that we can actually vary certain environmental elements, but not in a randomized manner, but in a semantically correct manner, because we have a grammar of this language. So it allows us to, it defines already composition rules. So with a sampling approach, we can then vary certain environments. So we're starting with a base environment, a base specification, and we can then vary the attributes of certain concepts, but also the composition of concepts. So a composition of a concept could be, for example, a room next to a room, and then this is possible in the grammar, and with the sampling approach, then we could basically define a certain distributions, for example, or certain limits of how many rooms should be next to each other, or to which degree, as you see here in this figure, the room is rotated, or what you see here in the darker lines, these are the wall width, which are things which can be modified. So starting from such a base specification, we can then automatically generate more advanced variations of this basic model. Okay, how does this look like? So on the left-hand side, you see this is the floor plan concepts which are available. So these are rather few concepts. Free space, which is surrounded by walls. Then we have dividers and entryways, which can be interpreted as entryways from one room to another, or windows. And then on underlying that, we employ standard geometrical semantics in terms of your coordinate transformations, which you all know from TF. So we describe these locations, so each of these concepts have a location, and this is described as a pose, and then through pose relations, we can then attach different space concepts with each other. Going now from these specifications, we want to actually automatically generate these simulation artifacts or assets. So in the background, you would start as a developer with specifying your environment with this floor plan DSL. You would generate variations, or you would generate just one representative environment. And in the background, this is just the front end. In the background, there's a knowledge graph representation, which you can also query. And this is the representation where we then also generate simulation artifacts such as gazebo world models for different simulators. So we are currently also supporting or working on supporting ISAC-Sim and other simulators. And this is all based on the knowledge graph concepts available in our tooling. The nice thing is that this allows us also not only to generate then executable artifacts, but also to compose new concepts. So for example, a concept about an articulated object, such as a door, would basically also operate on the pose concepts, which I have introduced before, but would be then a very simple model, but which can be arbitrarily composed into an existing floor plan model. And this is how it would look like, for example. So in that case, the robot is just driving through this corridor, and attached to these doors, there's a timing behavior. So this is now not related to the robot here in that case, where the doors are opening and closing, and then the robot needs to avoid that. And that is just by injecting one of these door and then doing quantifications over all of these entryways, and then automatically injecting these articulations into the environment, not by manually putting those things to the environment. What this also allows us to do is to infer higher order relationships between the robot and the environmental features, because this is actually what we are interested in. Yeah, we are interested in how does the robot react on situations in the environment. This is a very important thing, and this could be either humans or this could be articulated objects such as doors. And by having this in the knowledge graph representation, we have then a higher order relationship, which basically looks at what is the robot actually, and where is in that case, the door. And I give you an example here. So on the right-hand side, you see there's a robot in one room, and the task for this robot is to go to the other room. And the other room has two doors. And depending on the navigation system, it will make a plan to go in one of the through one of the doors. And in that case, you will see that the first door the robot is approaching is an adversarial door. So it is smashing right before the robot tries to enter the room. And that is achieved through having both a model of the static environment plus the articulated object and the robot, and then being able to actually compose various situations. Okay, so fine, but what does this actually allow us to do now? Looking to our methodology here, what we can do now is, okay, we are able to execute these scenarios, but what we actually want to infer is what are the actual acceptance criteria? Yeah? When do we know that this specific robot behavior, what you just saw, for example, with the smashing the door, is acceptable or not? Yeah? And this is something where you can try out many different case studies, and I'm going to show you some of those. These are, I have to admit, if you are working in the field of mobile robot navigation, these insights are not completely new, right? I mean, but this now allows you to actually check and validate upfront and be ensured that this is actually also happening in a specific environment, and to learn about the limits of your system. Okay, so that is the question. In order to do that, we need to have the execution in place, as you just saw. Okay, so let's start with one case study. So the one is what we also found out in the interviews was that developers said, okay, normally we first try to develop in a simulator with a recreated model of the target environment. Okay, good enough. But in some cases, this is tedious. Okay. One way to do this is if you look now to the almost 7,000 square meters in this real environment, and if you take maybe some architectural models and doing some own measurements, you are able to express that in these floor plan models. In that case, in a couple of hundred lines of floor plan models, where there is in fact a lot of repetition, so there is also a lot of possibility to even further do some automation. And this is nice because we can then use this representation and the generated artifacts to do some kind of a sim to real test, that we try to let the robot operate in the real environment, but with the map which we have generated, and vice versa. So this is a nice way to then test this gap. Another situation was when you look to the quotes, the worst possible case is a long corridor with repetitive few distinctive changing features. So this was a quote which we took from the interviews, and we drafted a scenario where we said, okay, we want to have a very repetitive and boring corridor. So with our Floban DSL, this is possible to say, okay, generate me now corridors of arbitrary lengths, for example, and starting at a certain point, certain lengths until another length. And in one of those scenarios, we identified a buggy situation, namely that the NAV2 stack actually underlying uses a Dijkstra path-finding algorithm to calculate the path. And one of the parameters for the path planning function is the maximum number of cells to be visited before returning the path. Yeah? But this value is actually hard-coded to be 4 times the number of cells in this created occupancy grid map, and this along the x-axis. And if this is not the case, then if a path is not found by then, the function returns an empty path. And this is exactly what you see here. And we identified that bug. And in fact, this was an 8-year dormant bug in the move-based local planner. And to validate this, if you just do a coordinate transformation where it's not along the x-axis, where you just switch it, then a path is actually found. So we also made, I think, a bug report to overcome that. Another scenario is that you can also then stress test certain situations, either scenarios with very repetitive or few distinctive features or very changing features. Situations like the one which you here see on the left-hand side, which is testing a bit the robustness, so the deviation between the real environment and the actual loaded map. And if you then intentionally place, in that case, it was motivated by a hospital environment where there are certain containers in the hospital logistic environments. There are suddenly certain containers on the corridor which are not expected. And if you directly next to an expected one inject such a container, then in that case, the robot immediately detects this container and the pose estimate in this case gets corrected. And the variance decreases almost to 0, but the robot is confident in the pose estimate, but the estimate in that case was wrong by, I think, 1.5 meters. Okay, so this is not a core insight, right? I mean, people working in this field, they know these kind of things, but it's interesting now that we can systematically reveal these situations. Okay, and then you can then try out different variations of clutter in the environment. Another thing what we tried out was one of the quote was to replicate the real environment, but then there's always the question when to stop. How much modeling effort should I actually put in? So this is a typical question one would get with these kind of approaches, that people would ask, okay, when should I stop to model? Because the modeling also takes some effort. If you take here now this real environment here on the left-hand side, then what you see here in the grid maps is, I think it's hard to see, but there are various levels of complexity or feature richness of the floor plan model. You can then also systematically test the level of complexity you would like to introduce into these models, and then relate that in a simulation campaign, for example, with the error and the variance of the pose estimate in each of these different environments. And then you see, for example, here that in the first one, of course, this is rather high than compared to the others. Okay, so this was now in the case where we do not know the acceptance criteria. So this was more in the context of also investigating the evaluation part more. But there are situations where we have actually a priori defined acceptance criteria. And these are sometimes coming from robotic standards. So, and what you then want to do is that you want to check whether your robot conforms to these standards. So that is what is called a conformance testing approach, or adherence to a system, of a system to a standard. What you would basically like to do is that you say, okay, given a certain robot, I have a requirement. The robot shall adapt, let's say here in that case, locomotion based on a certain terrain type. If you then look to standards, which kind of standards are actually out there and which of them actually define evaluation protocol. That basically means how to actually carry out this conformance test, right? The one thing is that I need to adhere to a standard. The other thing is a procedural specification of how should I actually carry that out. There are, in fact, also standards out there which do that. But the problem here again is that we do not have a level of automation. So this is now a quote from one of these standards to measure the distance between a robot and a concave terrain, including descending stairs and protective stops, etc. Yeah, so this is all described. And what we then want to, and these actually, these notions, what we can find here, and this is natural language. This is the problem, right? So it's then a bit difficult to automate that. Yeah. This we need to turn into an acceptance criteria which can be ensured. So how can we do that? Yeah, this is the question here in the conformance testing approach. Yeah, so we ask ourselves, okay, is it possible? To which degree is it possible to automate these conformance tests? Yeah. And we did an analysis of several of in the paper you can read more about them, the standards which we actually looked at. But we then specifically looked into these evaluation protocols. And that is quite interesting. If you now look to one of these clauses here, 15.4, it is distance of stopping before concave terrain. So, and if you do an analysis, you identify already certain concepts. The first thing is this test measures the distance. Okay, this is the objective of the test. Then we have a bit about the test subject. Okay, this is obvious, the robot. Then we have a bit of variability here. So what are the assets which can be used to test the system on? So here this would be the concave terrain. So what does this actually mean? And then we have a more procedural thing like including descending stairs after performing a protective stop. Okay, this basically means, okay, there is, after descending, I should perform a protective stop. So this is an expected behavior of the robot. And why we are doing this? Well, in order to evaluate the protective measures for a travel surface sensing. Okay, so that basically means if you want to conform to this standard, you need to have a hardware-software component in your system which does this travel surface sensing. And if you want to conform to it, then you need to carry out such a test. Okay, so we want to automate this kind of tests, and one way to do it is to do this in simulation first, and then maybe later also in the real world. And this is one approach is that similar to the floor plan DSR, we have now introduced a so-called robot test definition language, which allows us, which is a very tailored domain-specific language for these ISO 23482 standards, which actually captures exactly this concept, what you see here on the left-hand side in a test specification. But we have not yet answered the question of the acceptance criteria. That is namely, okay, what until when it is acceptable and when it's not acceptable anymore. And here we use a method from the software testing community, which is called property-based testing, which are high-level properties which must hold and which you can then use and compose with logical operations. So, for example, must be at, so that would be a property of a location, and not must collide. And these are high-level properties, and we actually found out that for I think 70% of the standard test here, we managed to actually play around with around 10 properties, high-level properties. So that basically means that there is some stability in these properties. We do not need to invent new properties. So there are many of those properties which we can actually reuse also for other test scenarios, which is a good story or a good message, I think. And then for the varying test, of course, then the actual criteria for these properties, they differ. So these are then the safety margins in those things which we want to consider. Then these need to be adjusted, obviously, for your specific test case. Okay, and the tooling allows us then also to things like the test what you see here on the left-hand side to perform certain tests with different robot configuration, different robot systems, but also certain assets which can be shared among these different test situations. We tried to realize the majority of these tests from speed reduction to stability test and so forth, and with varying robots. And in fact, for one of this robot, this is a Jekyll robot, the dynamic stability test actually on inclined surfaces revealed a defect in the driver, where the actual, when you restart the test, this only appears in software. We tried it out also in hardware. In the hardware, surprisingly, it's not appearing, but in software at that time, at least for this version, the expected behavior would be that the robot would move to the right-hand side, but the actual behavior is to move on the left-hand side, and this is due to a bug in the reset mechanisms of the driver software. Yeah, so this is, I think, a nice approach to automate these tests. Of course, this has also certain limitations, specifically when it comes that there are obviously certain tests which are defined here in the standard, which cannot be automated. Then there are also limitations of the simulation, which need to be considered, like fidelity and so on. But it gives at least already a good indication what are the things I should focus my development on. Okay, let me come to another topic that is what I just showed you now was the acceptance criteria which are derived by standards. But what about acceptance criteria which are application specific? So in fact, you want to develop your very own application, and then maybe you do not want to, or you do not bother to conform to standards. What would you then do? And then you need also a way to express those. And we looked into pick and place applications and how are pick and place applications actually defined. Surprisingly, there are very few specifications out there, so that's why we then looked into robot competitions, and we evaluated evaluation plans from various robotic competitions. And what you see here now for a pick and place task, to pick the object here, this cherry, to one of these containers on the right hand side. If you would specify such a thing in natural language in a competition like RoboCup at work, for example, in this case was it, then you will see that in fact there is some structure in it. So here we are talking in fact about the very same object. So object is in manipulation zone before picking. Robot holds the object. This is then the state further, right? We are still talking about the very same object. And we are also looking to the same assertion. So that in this case, while the picking or after picking, robot holds the object, and before placing, we are still talking about the same assertion, the same thing what we need to check. But this happens on different time scales. And this is a structure which you can find all over the place. This is for robotics people not new. But current testing approaches do not compensate for exactly that. So what we developed was, again, a specification language which allows us to specify such acceptance criteria. And what does it entail? So first of all, it is based on a framework or testing methodology, which is called behavior-driven development. Maybe some of you might be familiar with Gherkin. So this is one of the representative syntax. So it is used in software, web development, etc. But we look to those specifications, and they are, as I exemplified with this example, they are not rich enough to capture robotic scenarios. So what we introduce here now is an explicit timing specification in the form of fluents. So predicates with the time information. And such a thing is located at the location. Is the robot holding the object? Is the object released, etc.? These are things which we can express in these fluents. And then the BDD basically has three stages. The one is a given. So given a certain configuration of our scene, of our environment holds, when the robot is actually performing and carry out a specific task, and then a certain fluent holds true. So we have, if you are familiar with PDDL, for example, this is a bit like pre and post condition kind of representation, but here now combined in this BDD kind of frameworks with these fluent representation. And then another thing what we added here is that in fact we do not want to come up with a very specific specification, but we want to also introduce quantifiers, things like all. This is not shown here now, but this is the model allows us to do this. Sort all red cups into the specific container, or in the existence of an object, do the following. So these kind of expressions we can also encode here in this representation. Similarly to the floor plan model here, we then have also a front-end domain-specific language which allows the robot developer to specify its test, and a back-end representation where we have as an intermediate representation this knowledge graph. So this is good and this is fine if one can then actually specify these acceptance criteria, but we want to automate that. And we developed an automated test execution framework, which basically brings together our acceptance specification formalism, as I've just introduced, with Isaac Sim in an integrated manner. So this is what you see here now. So on the right-hand side in the console, you see the green and the yellow printout from the associated behave framework, which actually consumes our models and does the testing. And this is already in the acceptance criteria then are checked in the simulation environments. So this is our simulation-based testing suite. We tried out this on various pick and place scenarios, also object sorting scenarios, and then for different robots in different configurations, and checking certain pre-built controllers in Isaac Sim. But we are now moving also to the real robot to validate certain other kind of configurations. What you then here see on the right-hand side is, for example, the fluent regarding the end effector maximum speed and how it varies among the UR10 in Isaac Sim and the Panda for different workspace configurations. Workspace configuration here means like table height of the boxes, object sizes, etc. So all of this is also freely available. So if you want to try it out, please do so. Okay, last but not least, I would briefly talk about the generalization aspect. So I think in the generalization stage, it is important to consider, okay, what are the actual insights which I can learn? How can I generalize over a certain validation campaign? Yeah? And this is, I think, important in order also to come up with new benchmarking scenarios. Yeah? And benchmarking scenarios which are by definition stakeholder aligned. Yeah? So because we want to compare real systems on established benchmarks, but how do we come to these benchmarks in the first place? This is also a question which we need to answer. And I think one method is to actually use this methodology also to derive benchmarking scenarios. And these are quote unquote complete evaluation plans. Yeah? So generalized scenarios would be complete evaluation plans which cover a certain set of variation in the environment, tasks, and so forth. But here we are not yet on the level of at least for real physical systems that we have these evaluation plans being carried out in an automated manner. This would be really, I think, the holy grail, so to say, if we would achieve such an automation in the real setting. But what we can do is already use those evaluation plans, for example, as meta descriptions for data sets. Yeah? So if we want to have a justifiable selection of a data set, yeah, so in the context of this metrics project, we did this for handover scenarios and failures in handover scenarios. Yeah? Which were defined in these evaluation plans. So then this becomes a representative data set. And the decisions why certain features have been considered or have not been considered are then expressed in these evaluation plans. And this gives a bit of a transparency of these data sets and where these data sets actually come from. So I think this is an important step to make. Okay, but there are other ways also how could think in terms of this generalization. If you think, for example, for an individual system, like something like a long-term autonomy, and you run your system over a long period of time, and you would collect a lot of field data, and then which conforms to this scenario specification, which I just have introduced, then you could also generalize maybe insights. So this would be a more data-driven approach, but that is ongoing work also. Okay, so what are the capabilities and open challenges before I finish? So along these three dimensional stages, so in the specification phase, now we have these decorative composable models and an automated generation of parts of it. But still the open challenge is how can we come up with specification which really capture the real world semantics and the runtime insights. Yeah, so I think also on the specification side, we need to investigate this a bit more. The question here is also to which degree large language models, for example, in combination maybe with knowledge graphs could be helpful here in the specification phase. For the execution and for the analysis, the question here is it enables so far already a bit, not a bit, but a scalable automated scenario execution, for example, with this property-based evaluation, and it allows us already to uncover failure situations. This is exactly what we want. We want to uncover these failure-inducing scenarios in order to increase the trust in the systems. But still, we primarily these oracles are hand-written, and the question here is, are there any ways to maybe derive those directly from the specifications? things like runtime verification could be here very helpful. That from specifications we can maybe directly infer these oracles, which are then testing the system under or evaluating our system under test at runtime. You know? So that would be is also a very interesting research direction. And then also in terms of the generalization of the scenarios, so the first steps are made, but how can we automatically maybe derive complete evaluation plans, and how can we quantify the coverage criteria in the real world data? Okay, having said that, thank you for listening. And this is, of course, done not by myself, but not all of it at least, but by a small but amazing research group and some funding. And here are the tools if you want to try them out. Thank you very much. And I'm open for questions and discussion now, of course.